Hello guys, welcome. Thanks for being interested in my work. My name is Haowen Guan. I am a senior backend algorithm developer at DeepTracer, and I'm here to present my paper, DeepTracer-Denoising, for IEEE BIBM conference. This work is conducted under the supervision of Dr. Dong Si. In this presentation, I will start by introducing 3D electron density map and the necessary background needed to understand this research. And secondly, I will demonstrate the performance of DeepTracer-Denoising and compare its output result with other approaches, other tools. Thirdly, I will give an overview of DeepTracer-Denoising method, which is the prediction pipeline. And fourthly, I will briefly explain the training pipeline of the convolutional neural network model. And next, I will go over the dataset preparation detail. And lastly, I will briefly go over the evaluation result of our method. Here is a little background of 3D electron density map. 3D electron density map is 3D reconstructed from electron density images taken under X-ray crystallography or cryo-EM microscopy. Both methods are the mainstream method for visualizing protein structure right now. And the 3D electron density map is the direct result of protein figure under these microscopies. Here is the picture of the 3D reconstruction process. Since our research group are mainly focusing on cryo-EM microscopy, so from now on, by saying electron density map, I'm mostly referring to cryo-EM density maps. However, the X-ray crystallography density map are very similar, so our approach is generalized well to both approaches. Now we know 3D electron density map is 3D reconstructed from images, and cryo-EM images is well known to be suffering from the noise problem. So many cryo-EM image denoising algorithms has been proposed, such as Topaz denoise. All these cryo-EM image denoising algorithms are aiming at improving the signal to noise ratio, and their focus is to facilitate the 3D reconstruction procedure. Here is a picture of Topaz. However, there is an inherent problem of improving signal to noise ratio. That is, no matter how many times the noise is suppressed and the signal is enhanced, the noise voxel is still there and it cannot be eliminated completely. In this figure, it is a demonstration of noise after 3D reconstruction. Due to the inherent problem of signal to noise ratio, the noise is still presented after the 3D reconstruction, as is shown in this figure. We can observe the background noise and the structured noise, where the structured noise is defined as the ice matrix on top of molecular surface, which is formed during the sample preparation of cryo-EM microscopy process. And also, the second scenario is the unproducible conformation variation of protein. Here is the same map showing in camera X. We can see the blue one is the ground truth protein structure, soft protein structure. And if we drag the level bar lower, we can visualize the density map. And if we go lower in the level, we can observe the structural noise in a ring shape, which is apparently not part of the structure. And if we go even lower, the background noise will show up. Here, we can start by showing the background noise mode denoising of DeepTracer-Denoising algorithm. Here is the output of background noise mode. It's presented in transparent yellow. We could also show the protein structure. And as usual, we drag it from high to low. The structural noise still show up because we are using background noise mode. But if we go lower, there is no background noise. We could compare it to the original map. Nextly, we can demonstrate the structural noise mode. Here, the output is presented in transparent green, so we can compare it with the structure. in this output, we can observe that the ring-shaped structural noise is successfully eliminated. We could also compare our result with camera X height dust 2. Here can be found here. First, we can visualize the original map noise. Then we can enable the height dust tool. Camera X can denoise some certain degree of noise, but when the level goes lower, the noise still shows up. And if we go even lower, the background noise will still show up again. Like this. Here we will go into our implementation. We will first give an overview of our method, which is here is the prediction pipeline. To do the prediction, the only input needed is the cryo-EM density map. And with some pre-processing, such as normalization, after that, we can cut the density map into a 64 by 64 by 64 cubes, a unitary size, and input it into the 3D UNet with pre-trained weight, and we can reconstruct the cubes back to the full map. And then here is the output of the UNet, the deep learning network. And we can use this output as a mask, and then choosing a certain threshold, so we can classify each voxels as being as part of the structure or noise. Use it as a mask, we can filter out, manually setting all this noise value to 0, and then finally given a clean map. For training procedure, it is very similar to prediction pipeline, except that there is no masking procedure. So for training procedure, we need the pre-processed input map and then name it as X. And then we will also generate a simulated map to make a target map Y. We will be training the 3D UNet to map the input map to a target map, and which is essentially a voxel-wise classification task. In terms of training set, we collected 1,739 density maps from cryo-EM databank. Then these maps are further split by 80:20 ratio to training and validation set used for the training. And the whole data set is about 489 gigabytes. Here is the detailed architecture of our network. It is a modified version of UNet, which is a very popular one among the biological community. The original UNet is a 2-dimensional convolutional network. To use it on 3-dimensional data, we converted it to a 3D UNet, as shown here. Next, we will go into the dataset preparation procedure. Dataset preparation is the most important part among of our approach, since in order to train a correctly functional deep learning model, we need correct data pair to fit into it. However, in reality, the data pair is not ideal sometimes. For example, as figure showing here, the density map is showing in a rectangular shape, this gray one. However, the soft structure, which is the middle red part, only covers the center middle part of this density map. It is not a complete PDP in terms of this density map. The complete data pair should look like this, that the protein structure is exactly the same figure, and it fills the whole density map. In order to distinguish the incomplete data pairs from complete data pairs, we proposed a similarity metric, which is based on correlation coefficient. And this value can be calculated automatically, and with the output value. For example, for this metric, the metric value of the similarity of this data pair is only 0.16, but for this data pair, the similarity gives 0.85. So with using this value, we can automatically filter out the incomplete data pair by throwing away those pairs with low similarity. After dataset filtering, we will be generating our input X. We just take the original map and resample it to 1 Electron voxel grid to unify the voxel size and normalize each density map to between 0 and 1 value. Then we cut the density map to the unitary size of 64 cube, same as we mentioned before. And this is a processing of input X. For target Y, we will be simulating density map from PDB file. With the simulated density map, we convert it to a 1, 0, and 1 mask. By saying 0, 1, this mask only contains 0 and 1. It's just like a one-hot encoding. And we'll be using this as the ground truth for voxel-wise classification result. And the training data is just the pairs of input X and target Y. After training, we did some statistical about our final model. We draw the precision recall curve and used the G-mean metric to calculate an optimal threshold. We found there are two optimal thresholds. The first one is 0.035 and the second one is 0.495. We found out that both thresholds works great in different scenarios, and we eventually classified them as background noise mode and the structural noise mode. To evaluate our model's performance and generality, we further collected 349 density maps from Cryo-EM databank, which are newly deposited after we build our training dataset. During the evaluation of background noise mode, our model achieved a precision of 99.87% and a recall of 97.7%. And with using the structural noise mode, our model achieved a precision of 99.27% and a recall of 99.64%. Detailed evaluation and explains and a data pair-wise model can be found in the paper. Finally, thanks for interest in my work. This work will be added to DeepTracer website as a tool, and we encourage everyone to give a try. Nonprofit user can register our account for free and use all our tools online with cloud server computation. This is a citation of some image I used. Thanks for listening again. Bye-bye.